Welcome to the Minnesota Stormwater Seminar Series. I am John Gulliver, and I will introduce the seminar series and our speaker. This series of seminars is co-sponsored by the Water Resources Center and the San Antonio Falls Laboratory, both at the University of Minnesota. The funding for this seminar series comes from the Minnesota Stormwater Research Council. Our speaker today is Dr. David McCarthy, an associate professor of civil engineering at Monash University in Australia. David's area of research is the biosurveillance of pathogens in urban stormwater systems and the subsequent methodologies required to manage pathogens to protect human health. He has specialized skills in water microbiology, risk assessments, pathogen fate and transport, urban hydrology, stormwater management, green water treatment technologies, and water quality processes. David has an active research program. He established a microbiology laboratory, which now hosts 25 research technicians, research fellows, and PhD students. He is currently developing a real-time sensor arrays for understanding urban water system dynamics and modeling together with the real-time monitoring and control of stormwater treatment measures. Finally, he has received 2 awards for his 3D printed passive sampler, which has been deployed more than 30,000 locations around the world to monitor SARS-CoV-2 in wastewater, thus helping protect many lives from COVID-19. David is very active in international stormwater service, including being the chair of the 2021 International Conference on Urban Drainage, which was held in Melbourne, Australia, and the current chair of the International Water Association and International Association for Hydraulic Research's Joint Committee on Urban Drainage. Today, David will talk about his efforts in simple real-time monitoring and control of stormwater green infrastructure systems. So it is my pleasure to welcome Dr. David McCarthy.
Thanks, John, for that marvelous introduction. I really appreciate it. Yes, as John mentioned, I'm David McCarthy, and I come from Melbourne, Australia. And today I'll be talking to you about activating green infrastructure for improved treatment. I come from 2 labs, as John mentioned. One of them is the FM lab, which is a microbiology lab we established in the civil engineering department, and another group called BOSSL, which is working on developing low-cost sensors and control strategies for stormwater management. Obviously, a lot of my work today is a nice summary of lots of people's input, and I'd just like to first thank all of my fantastic staff members, past and present, and all of my great PhD students who have made what I'm going to present to you today possible. So thank you to all of them. A little bit about me. John mentioned a little bit, but just a little bit more, just so you know who I am and put myself in context. So I started my PhD in 2006, and at the time in Australia, we were in a significant drought, one of the worst droughts we've experienced. And trust me to pick a topic of having to sample stormwater during the biggest drought on record. That was quite difficult. So my PhD was understanding human health risks of recycling stormwater, where we did a lot of monitoring when it did rain and a lot of modeling. So during this PhD, we were really trying to understand what were the contamination levels in urban stormwater, and therefore how much do we need to treat stormwater before we harvested it, so that we could help reduce the impacts of this terrible drought I just mentioned. I went on to a research fellow role for a couple of years, which is more like a postdoctoral fellow role, as you guys would say. And during this time, I worked on a number of different treatment systems for understanding and mitigating human health risks for stormwater harvesting. During that time, we developed some very nice treatment systems and explored how we could reuse stormwater in a safe and meaningful way. Since then, I've been an academic in the academic institution of Monash University. So my research interests, and I like to kind of look to Scopus to see who I am. This is Scopus plotted on your country just to the north of you, Canada. I'm part Canadian, that's why it's in the Canada map. But as you can see, I'm a stormwater guy. I love to play around with E. coli, which is a common indicator organism for fecal contamination. And I love to play around with biofiltration systems and do catchment modeling. So my research area is really integrated water management with urban hydrology, stormwater management, green water technologies, and water quality processes. And a lot of my focus, a lot of my research is kind of contextualized around the fact that we need to harvest and reuse urban stormwaters to make our cities more resilient against climate change and population growth. And I love things that are trying to protect human health. So a lot of my work focuses on protecting human health. And so removing those pollutants of concern, in particular pathogens, those microorganisms that can cause disease to humans. So cast yourselves back to 1997. Some of you might not even been alive by then. And in that time, we had a beautiful dam built called Thompson Dam, and it was full to the brim. During my PhD, as I mentioned, we were down to just 20% of our storage supply for a big city of almost 4 million people at the time. So there was a lot of emphasis on recycling of waters. And indeed, urban stormwater previously had been considered as a nuisance, something that we needed to get rid of, something that we needed to remove from our urban areas because it was unsightly and could cause risk to humans. During 2008, that changed. Urban stormwater became a thing that could be reused. It was a resource. So we wanted to transform this idea of just flushing it all down the drain. We wanted to put it through treatment systems. This is one of the earliest water sensitive urban design or green infrastructure systems that were built in Melbourne. It's a nice swale in the Limbrook estate. We wanted to trap the microbes and the things that could harm us in these treatment systems. Once we trap them, we want to kill them so that we can then safely reuse the water that comes out of those treatment systems. Maybe not for drinking water, but certainly for things like garden irrigation and perhaps toilet flushing. So to begin with, we thought, well, let's have a look at the existing performance of green infrastructure systems. How were they actually working? We wanted to understand whether these existing designs that were designed mainly for treating things like nitrogen and phosphorus and sediments, how they were performing for microbes, these pathogens of human concern. So we started to look at multiple wetlands around Melbourne and Victoria. And this is just some of the results that we got from one of my students, Mia Meng. She looked at 2 microbes, E. coli, which is a typical indicator organism, and Campylobacter, which is a common disease-causing microbe. In fact, in Melbourne, it is the leading cause of GI illness or gastroenteritis illnesses within Melbourne. So a very important microbe. On the y-axis here, you see log reduction. If you're not familiar with this, 1 log reduction means 90% removal. So if we have 1,000 going into the system, we have 100 coming out. 2 log reduction means 99% removal. 1,000 in, 10 coming out. As you can see, E. coli is consistently removed. Over 22 storm events, we monitored very, very precisely in the inlet and the outlet, and we found very good removal, generally around 90%. However, look at Campylobacter. Sometimes we were getting pretty good removal, 90%, and then sometimes we were getting almost 90% leaching. So we were getting more being produced within the wetland than was actually being removed. How frustrating. Not very good when you're trying to reuse the water that comes out of a wetland. We also monitored biofilters, and we had a look at the literature surrounding biofilters for different pathogens and indicator organisms. And again, we noticed quite a lot of variability, ranging from net leaching, negative removal rates, to overall positive removal rates. So we thought, okay, we need to better understand what was going on within these systems, and perhaps if we improved our design, we could potentially improve the amount of treatment that was going on. I'm just going to check these chat boxes to make sure that, no, you never know, they could be something like, David, we can't hear you. So improved design equals improved treatment. We wanted to optimize the design of these biofilters so that we could potentially reduce that variability that we saw on the previous slide and increase the overall treatment efficiency. So if you're not familiar, I hope you all are, but if you're not familiar, this is a typical biofilter system. We have vegetated system. Inside here, we have some media of some description. And often what we will have is this raised outlet, allowing us to have a submerged agnostic zone in the bottom of this system, which supports plant growth during drought periods, but also supports a whole range of microbes to help with perhaps denitrification and nitrification processes. What we want to do is trap the microbes in this biofilter and remove them more efficiently. And so we began our journey by looking at different design factors. How can we optimize the plants? What about the media? Does the submerged zone improve pathogen removal or does it not? Along came my next student, Gayani Chandrasena, who looked at different types of plants. These are all the different types of this concept of log reduction, 1, 90%, 2, 99% removal, and so on and so forth. What she saw here was that there was a tremendous amount of variability in the removal rates. But overall, she found that shrubs generally had a higher level of removal than the other plant species that we looked at. She also noticed the influence of the submerged zone. And as you can see here, in some circumstances, having a submerged zone significantly increased the overall amount of removal than without a submerged zone. So the green box plots here represent those without the submerged zone, and with the submerged zone are the red box plots. So you can see the red box plots are generally higher than the green, and it was statistically significant. Then we thought, okay, maybe there's some other plants that we could trial, in particular for pathogens. And if you don't know already, but everything in Australia seems to kill you. We have little spiders that kill us. We have little snakes that kill us. Everything is dangerous. Turns out our plants can also be dangerous. And Penny and Miriam both looked into different types of Australian native plants that could potentially exudate antimicrobial compounds into the soil and into the leaf material that gets deposited on the surface of the biofilters. Penny and Miriam both looked into this and discovered that indeed these callistemons, leptospermums, and melaleucas, all very typical of Australia and New Zealand, have quite an effect on the survival properties of bacteria. So we designed biofilters with these plants in mind so that we could better inactivate these microbes. The good news was that we could get the benefit of inactivating those microorganisms while at the same time maintaining the great removal rates of both nitrogen and phosphorus through these biofiltration systems. Yali Lee came in and said, well, what about the media? Could we optimize the media of these systems to better capture the microbes? And then once we've caught them, kill them. And indeed, she found lots of different materials that could capture the microbes better. And she found that, for example, copper, no news to almost any of you, copper has been used for centuries as an antimicrobial compound. This copper can kill those microbes very quickly. So she spent years of her life designing a stable coating process on different types of materials to ensure that copper wouldn't leach into the environment. She tested this in this sophisticated laboratory that you can see here, and we observed hardly any copper leaching, even after 2 years of experimentation. She saw extremely good removal of E. coli and Campylobacter through these systems. And she also noticed that in a field trial, we weren't leaching any copper from these systems. So after all of this design optimization, all of this work that we went through, can we now safely harvest stormwater? To test this, we applied what we called a quantitative microbial risk assessment. I'm not going to go into the details of that today, but we basically looked at how well these pathogens were removed through these biofiltration systems, and then modeled that to predict what the outcome would be if people were to use that water for, let's say, toilet flushing or perhaps irrigation. We compared those results to the Australian guidelines for water recycling, in particular the guidelines on stormwater harvesting and reuse. Unfortunately, as indicated by this title that we published a few years ago, we found that the existing treatment technologies that we were using to remove pathogens in urban stormwater were still unable to meet the objectives of this particular guideline. So even after all of this effort and all of this work in optimizing the design, we found that harvesting of stormwater was still unable to meet local guidelines. What a shame. But we learned a lot through the process. And it certainly wasn't a waste. So then the question becomes, okay, our improved design didn't really improve treatment. That's a bit of a shame, but why? What's going on? So we go back to Gayani's little slide here. You can see here the variability that I mentioned earlier far outweighs any of the benefits that exist from changing the different plant species, but also whether we have a submerged zone or without a submerged zone. Meaning that independent of whether we select the best plant and we have a submerged zone in the system, the variability of the operational conditions of the biofilter were so large that which basically meant that the overall performance of these systems were dictated not by design, but perhaps more so by operational conditions. That was a revelation for us. We understood now that these systems, not only do we have to have good design, but passively, these passive systems without control were unable to meet the strict regulations, such as those of health targets for reuse guidelines. So we can't ignore the operational conditions of these systems. Gayani put together this beautiful slide deck, and I'm going to share it with you today, kind of trying to allow you to understand why operational conditions are so important for these little microbes. Today, I'm going to introduce you to this guy called Eddie the E. coli. Unfortunately, our objective today is to kill Eddie. So it's a bit gross. We want to kill this little guy. We want to trap him, and we want to get rid of him as quickly as possible so that we can protect human life. Let's say we have a beautifully clean biofilter and a wet weather event comes in and we inject all of these eddies into this biofiltration system. What happens first is that old water that sits at the bottom of the biofilter is pushed out hydraulically from that biofiltration system. As those eddies migrate through that biofilter, some of those, actually most of those eddies will be trapped within the biofiltration system itself, which is great. A couple might escape, those sneaky little buggers. In this process, we have quite good removal because we have good absorption, clean old water gets pushed out, and we're getting very good removal rates, thus indicating these high removal rates that might occur during monitoring of field installations. During a dry weather period, those eddies will begin to die off. And so after 3 days, you might have half or even less, maybe even 90% less than what you had originally on the first day. Let's say we have another wet weather event at the end of that particular dry weather period. Let's pretend that there were no eddies in the inflow. That blue box up there is eddy free. If we put that water through that system, that E. coli or that eddy that was in that old water might get desorbed and move to the outlet. And perhaps even that eddy that was right at the top could also get desorbed and move to the outlet. So in this case, we had nothing going in, but we have two eddies coming out. So we have desorption. And unfortunately, under these conditions, we potentially have what we call leaching. So we have more coming out than going in. Obviously a big problem, and perhaps is the cause of some of these negative removal rates that we saw during our field monitoring days. What we did next was that we used this information to design real-time control strategies. We realized that if we were able to manage the amount of time that water spent, or these eddies spent in the biofilter in a very controlled manner, we could optimize the overall performance of the system to avoid what we saw, which was that desorption. So in this case, if we could extend it to 4 days, perhaps we could remove all those eddies before the next wet weather event, and therefore no leaching. Wouldn't that be terrific? So along came Pung Fei Shen, who was a terrific PhD student who started out on this journey of looking at real-time control of biofilters for pathogen removal. So he recognized Gayani's work and he said, well, if we can control these biofilters better, then perhaps we could achieve a better pathogen reduction. He looked at implementing cheap and simple strategies to control these systems, and he did it mainly in the laboratory. And he used simple actuators paired with Arduino devices to control how these systems were operating. He developed two strategies that I would want to share with you today. The first strategy was this concept of harvesting only the best quality water. So what he focused on here was ensuring that we had enough retention time in that biofilter after the previous wet weather event to ensure those microbes were dying off effectively. So his strategy was quite simple. He had only two things he had to change about the biofiltration design. The first one was a flow meter. We don't like this strategy too much because flow meters are expensive, but we've designed little flow meters now that can sit outside of the water column and can have a non-contact way of measuring velocity and depth. So we're trying to change the way in which monitoring is done and make it cheaper. So a flow meter might be more possible now. He also has a valve at the top and a timer, just to time how long the water has been sitting in the biofilter for. The only strategy, it's an algorithm-based strategy. He times how long the water has been in that biofilter for, and if that time is less than the minimum threshold that he sets, let's say 12 hours, then the system is bypassed. We bypass the stormwater to the environment, which is a big shame. Doesn't mean that we're protecting the environment, but what it does try to do is mean that we get very good quality water to harvest. So in this case, just to repeat, what he's doing is he's got a valve, and that valve operates in a way which ensures that the duration of contact that the water has had with the biofilter is at least, for example, 12 hours. If it hasn't had that 12-hour contact time, the water is bypassed around the biofilter. If there's a new stormwater event, it's bypassed around the biofilter to maintain the length of time the old water is being in contact with that biofilter. So he started to model this first. He developed quite a complicated model. He validated it against lots of previous data that we had, both field and lab data. And he began to model this first strategy. So these are modeling results right now. I'll come to the lab results just in a moment. On the y-axis, again, you see this concept of log reduction. So 1, 90%, 2, 99% removal. The first box plot you see there is for non-real-time control. So the normally operating biofiltration system, operating as normal as a passive system. Getting about 1 to 1.5 log, which kind of matches what we were getting in our experiments. And then as we move along the axis there, you see T1, T6, T12. These just represent the minimum duration that we ensure the water is sitting in the biofilter for. So if a stormwater event comes, that water has to sit in that biofilter for at least 1 hour, T1, 6 hours, T6, or 12 hours, T12, so on and so forth, up to 2 days. If the water hasn't been in there for that period of time, remember, it's bypassed around the system. So with this, we estimate that with no real-time control, we could probably irrigate our municipal ovals and areas with recycled stormwater. But we really don't want that. We want to push this further so that we can start using it in and around our houses. So Pungfei looked at how we could control things to make that happen. These are the rest of the results. So don't get too inundated with what's going on. Let's just focus on, for example, T12 versus the non-real-time control. T12 box plots that you can see here, these represent a minimum of 12 hours of water sitting in that biofilter since the last event. Any event that comes within that 12-hour period is bypassed. If it's been more than 12 hours, then water will allow it to flow into that biofilter again. you can see the significant improvement in log reductions just by maintaining that 12-hour window, which signifies that it's really the back-to-back events that cause the leaching of these microbes in these ecosystems. So we're getting almost a 2-log reduction increase, which is a 2 orders of magnitude increase in removal of microbes, which is excellent. But as with everything, there's trade-offs. When we had a passively irrigated, passively designed system, we treat around 90% of the inflow volume, meaning that 90% of what comes into the system is treated and only 10% is bypassed. As we hold the water in there and manage that water more actively, obviously, if we're ensuring that we have a minimum duration of contact of 12 hours and bypassing the rest, then obviously we're bypassing quite a lot. In this case, in 12 hours, we're bypassing almost 60% of the water to the ecosystem. So we're not treating 60% of the water. Here, we were not treating 10%, which is pretty typical for biofilters. You know, those large events are hard to treat. But here, we're bypassing 60%. That's quite a lot. Nonetheless, even with that trade-off, the quality of water that was coming out of the biofilter was such that we could reuse it directly for stormwater harvesting purposes, like indoor toilet flushing and household irrigation. What a fantastic outcome. Hollenhorst said, okay, these are just modeling results. Let's take this to the lab and check out what happens if we did this in the laboratory. So he tested 2 scenarios. He had 5 columns that were T12 scenario and 5 columns that were not real-time controlled at all. He found that no real-time control was just outside of his modeling results, and the removal rate for the T12 situation in his lab work showed that it was just within his modeling, one of those outliers you can see there. But the difference in the removal rate was still about the same, about 2 orders of magnitude, 1 to 2 orders of magnitude. So the lab results somewhat confirmed what his modeling results showed, but in particular showed that we had a very good overall removal of pathogens through the system during this real-time control strategy. He's published this in Water Research, and so if you're interested, go and have a look. All of the other stuff that I've mentioned today is also published, so search for my name and you'll be able to find it. Hollenhorst said, well, this idea of bypassing all of this water was not really great. Let's see if we can kind of co-optimize having some water for harvesting, but also still treating as much water as we can. So we designed this concept of a balanced system. In this particular system, what he had was a timer, but also what he did was he had 2 different outlets. He had one at the top of the submerged zone, which discharged to the environment, and one at the bottom where a valve existed where he could drain the system before events came to a stormwater harvesting tank. In this case, he needed some idea of weather predictions. In condition 1, if the rainfall is predicted, if there's rainfall predicted and the detention time within the biofilter of that old water that sits at the bottom of the submerged zone was greater than 12 hours, then open that bottom valve and drain it to a tank, a harvesting tank basically, where we can connect to and reuse from. At some point, once that is completely drained, we would close that bottom valve. We know how much volume is in the bottom there, by the way, so we can measure the increase of water depth in the tank to then say, okay, once that's all drained, let's close the valve and allow the normal operation of flow to occur to the ecosystem, meaning that we're not bypassing the water anymore. We're just allowing it to drain first and then go through that biofiltration system. If the water hasn't sat in that biofilter for more than 12 hours, then it just operates like a normal biofiltration system. So the results of his strategy 2 were quite promising. He took it to the lab again. He found out that we could harvest about 5% of the total annual rainfall or volume that came off our stormwater catchments. You might think, oh, that's pretty small. Yeah, sure, we could probably optimize this more. But importantly, the removal performance cleanliness of that water that drained at the bottom was amazing. We were talking 5 orders of magnitude difference between what was going in and what was coming out. Very suitable for harvesting directly. We found that we were able to still process 83% of the volume that came into the system, so that we weren't bypassing as much. We're only bypassing now about 17%. And even with all of that, we were still achieving at least a log reduction in E. coli before discharging to that environment, which could be used for example, recreation. So RTC on biofilters works. We think we can make it work. But what about wetlands? How do wetlands work with biofiltration systems? On to our next student, Shi Xue. Her work is about wetlands and pathogen removal of wetlands and controlling them using real-time control strategies. She set up 6 systems, and as you can see, they're very happy in this greenhouse, looking at 3 that were real-time controlled and 3 that were normally operated, i.e. passively operated. She kitted them out with all of these different sensors that we've been developing in our group: turbidity sensors, depth sensors, temperature sensors, EC sensors, flow meters, all this kind of stuff. And she looked at how they were performing both hydrologically, but also from a water quality treatment perspective. She also tested 2 strategies. Pretend this is our wetland. Her first strategy here is an outlet closure strategy. When we observe a small increase in water level within the wetland, we automatically shut the outlet. And we shut it for, in this case, in our case, we shut it for 24 hours. We haven't optimized that yet, but that was our first guess. We closed it for 24 hours. Once that 24-hour closure time had occurred, we then open that outlet and we drain it at a quicker rate. We drain it so that the total drainage time of a passively operated system, one that operates without real-time control, and one that operates with real-time control, have the same drainage durations, total drainage durations. So in this case, what we're doing is we're effectively increasing the retention time of that newly input water. In our RTC strategy 2, we use this concept of pre-drain. If we have, in this case, unfortunately, we need some rainfall forecast. And again, she's assumed it to be perfect, which is very difficult to do. So we don't like this strategy as much. She pre-drains the water based on that rainfall forecast, and she does it up to a level of 30%. That 30% allows enough capacity for the next event to come in, but ensures that we don't drain so much that resuspension of bed sediments would occur. So a maximum drainage rate of 30%. Then the water comes in and that wetland and continues to operate normally. So in this case, we both increase the retention time, but also the wetland capacity to treat incoming waters. In real-time control strategy 1, her laboratory work shows quite a significant improvement of E. coli log reduction. Again, the y-axis is log reduction here. The blue box plots represent a real-time controlled wetland, or the 3 real-time controlled wetlands, and the orange box plots represent the passively operated or the non-real-time controlled wetlands. You can see again here we're getting on average about 1 to 1.5 log reduction improvement. So it's 1 to 1.5 orders of magnitude improvement from our real-time controlled columns. From an E. coli load reduction perspective, so the left is E. coli concentration reduction, on the right is the overall load of E. coli being reduced. You can see the real-time control strategy is very, very, very effective and reducing the variability of how much is actually being removed in terms of the total number of organisms. So we would say that this is a pretty successful real-time control strategy and very simple. No rainfall forecasts required, just need a valve at the outlet and a depth sensor in the wetland to make it work. The pre-drain strategy worked okay, maybe not perfectly, but still we were happy with the results. We see here again, y-axis is log reduction, and this is for E. coli, so instantaneous E. coli, EMC, so event mean concentration inflow compared to the outflow event mean concentration. You can see that we're getting roughly an order of magnitude increase, but much more variable. Same thing here. In this particular scenario, we had a slight increase in E. coli load reduction, but not as significant as we saw before. So this is all great. We've got some good evidence to say that we can simply real-time control these systems in the laboratory. But get real, what about what about in real life? What about doing this in the field itself? Luckily enough, just a few weeks ago, we were awarded an ARC government grant, which is similar to your research council. We're going to start real-time controlling these stormwater wetlands in the field. And this particular is super interesting. And the outlet and we've developed. We've got some sensors that are radar sensors that we can detect both water depth and velocity. We've also got opportunities to use our new low-cost turbidity sensor, which costs $30 to monitor turbidity through the system. And we've got a logger system here that is low cost as well, which is NB-IoT activated. So the idea here is that we're going to model this system in a very complicated way using two-flow and this concept called AED2 to model microbe behavior. And we're going to use the outputs of that particular, those models to design very precise real-time control algorithms. So just a couple of conclusions. So first of all, the design and operation are both essential for wetlands and biofilters. We need good design, but we also think that in the future, careful operation and real-time control of these systems might make them more resilient to climate change effects, land use changes, population growth, etc. Real-time control can help improve pathogen reduction in both stormwater biofilters and wetland systems. But as always, there are trade-offs that we need to consider. Like in Pungfei's example, where we had this biofiltration system, he was bypassing lots more water so that he could get improved treatment outcomes. There are other things to consider, including pollutants other than pathogens. We need to make sure that we don't compromise the removal of those pollutants. Finally, we need to acknowledge the fact that this is making things much more complicated. We're having a much more complicated system with real-time control elements. In future, we want to work with our industry partners in workshops to design new strategies, take them back to our models, model the outputs and convey those outputs back to our industry partners. We're going to design things called model predictive control algorithms and also just algorithm-based real-time control strategies with and without forecasts. We're really not a big fan of having forecasts in our model predictive control because it makes it much more complicated and more uncertain. We're going to continue our sensor development and we're really excited by the low-cost nature of our sensors that we're developing so that we can fit out our real-time control systems so that we can monitor them very carefully. We're going to start field testing both biofilters and wetlands for real-time monitoring and control. And we're going to do this in a really slow way, incremented, staged approach, so that we can slowly build the confidence in the control strategies with our industry partners. Because these large assets, if they're controlled in the inappropriate way, can cause devastating effects. We need to make sure we have fail-safe systems that are being designed, that if they do fail, they're done in a way which is safe. We're going to develop methods and guidelines as well, so that if people in the future would like to test real-time control, they've got some guidance materials. Just wanted to highlight a few other people like Kafung Zhang, Tim Fletcher, Fred Shirky, Southeast Water, Branko Kirkutz, and John Hathaway, all of which are experts in this field. And so if you're interested in real-time monitoring and control, it's probably a good idea to check out these guys. Not a very good gender equity here, by the way. And I apologize for that. I didn't do that on purpose. I just noticed it then. The IoT for Water Hub is a hub that we're trying to bring together lots of different research themes about Internet of Things for water. And if you're interested in joining that hub, I would love to have you on board. Please visit iotwater.com.au. Just like to finally acknowledge all of my students and staff, past, present, and future, and my teams in the FM Lab and the Bossel Group. My funding from Department of Health, Melbourne Water, PA, and Research Council from Australia. Thank you very much for your attention, and I'm so sorry that my internet has failed me.
It's as Andy said, it could be just a supply and distribution problem, so affecting the internet.
No worries.
So we have some questions. The first question comes from Jim Lenhart. His question is, what variable aside from time impact pathogen removal? For example, temperature can result in seasonal differences in removal rates.
Fantastic. Yes. John, can you hear me okay with my video on?
I can.
Okay, perfect. Okay, good. Thanks, Jim. I follow your work a lot, so thanks for the comment. You're right. We started out really at this most simple side of things. We're really simple people. We love simple operation. You're completely right. Temperature is an important factor. We could monitor the temperature throughout the biofilter. We could also monitor soil moisture. Soil moisture is a critical thing that keeps microbes alive. More moisture, they're happier. Less moisture, they die more. So that's also an important factor that we could start monitoring within our biofiltration columns. So temperature and also, I would say, soil moisture within the system as well. We've started to look at irradiance, so light, the amount of light that's around that is also a very good way of disinfecting microbes. We find that a lot of the microbes sit at the surface of these biofilters. They get trapped in the first few centimeters. And so temperature and irradiance of that surface and moisture content of that surface that evaporates the quickest will be all very important factors. So Jim, great. Maybe that's the next stage.
Okay, that's great. Now, we also have a question from Dale Brown. David, thank you for a great presentation. The results suggest we may be letting water pass through biofilters too quickly. Should we consider limiting outflow capacity even in assets without RTC? Do you see similar results for nutrient removal?
Great, thanks, Dale. So I think I'll answer those in separate ways, if that's okay, Dale. Yes, I do think that if we can slow the outflow rate of these biofiltration systems down, then we're going to have a lot of differing effects. So number one, you're probably all aware that clogging layers form on the surface of these biofilters quite quickly. Those clogging layers means that we have an unsaturated flow process that goes on beneath those biofiltration systems. And I think that's not a healthy thing for good pollutant removal. So if you really wanted to optimize pollutant removal, perhaps we could restrict the outflow. That could benefit in many ways, increasing contact time, but also increasing the contact actually with the water in a saturated sense instead of an unsaturated sense. So yes, Dale, I agree. We try to make these designs as simple as possible, meaning that if we could access the outflow pipe, we could easily control that outlet. So Dale, I agree. Your second question, John, can you just remind me of that second part of the question?
Do you see similar results for nutrient removal?
Yes. Yes, the answer is the increase in performance is not as significant as what we've seen for the pathogens, but we certainly see at least a maintenance of the removal rate, and in some cases the increase of both nitrogen and phosphorus. Sediment doesn't really change with real-time control, it's just effectively removed, independent of real-time control.
Okay, I have a couple of general questions. Well, I'll try and get through these very quick. First, about wetlands. You know, you use the bump above the wetland as storage for the 24 hours. But what happens if you have a really big storm?
Yeah, I think during large events, if it's really big, if you're talking more than one in 1 year or something like that, this is what we kind of design out.
A 3-year storm or something comes through.
Yeah, I think at that point, there's probably all bets are off in terms of being able to do anything meaningful, I think, from a water quality perspective. I think that we're exploring whether these systems could be more or better controlled during flood events. I don't know if you've heard, but in Queensland, for example, and New South Wales in Australia, we've been having some severe effects and rainfall events causing significant flooding. During those events, I think we're not going to have much of an impact. But with more small 1 to 1 year, 1 to 5 year, I think we could optimize. But at the moment, with the strategies we've got, they're not going to do anything. The only thing we could do is bypass water from around the wetland, perhaps, or
Okay.
we're not focusing on those large events. That's a hard one.
My next question is about shrubs. Why would shrubs have a greater reduction of pathogens? Do you know?
Yeah, great question. Yeah. So what we found was that in particular with a couple of species, those shrubs have really aggressive root growth. And so their growth rates were aggressive and their root occupancy was very, in particular for fine roots, were very aggressive. And so their occupancy rate of the soil was significant. We think that helped create biofilms. We think that helped create macropores also for movement of water. But in particular, we thought that might potentially help with creation of particular uptake points for phosphorus and perhaps conversion points for some of the nitrogen cycle. So that's our hypothesis. We did see relationships between overall mass and length of root in our biofilters and linking them back to the removal rates. So that's what it was with those shrubs, aggressive little buggers from Australia.
So the last question comes from Anna Barker. The question is, how can citizen science monitors here in Minnesota or in the United States become connected with your work in Australia? She asked you to repost the hub link again.
Sure thing.
That's what she's looking for. Excellent.
I'll do that right now. And if you want to reach out to me, I'll put my email as well into the chat box. and please feel free to reach out, and I would love to connect, because I think citizen scientists, we've been touching on that in Melbourne a little bit, being able to use citizens to tell us when the biofilters look not very nice, but also when there's lots of ponding water for excessive periods of time. So this is beginning to be looked at, but certainly not something that we're good at. So I'd love your input there, and connection would be great.
All right, great. Thank you very much. We have a break coming up, but a panel discussion, which I think will be really interesting, is going to come back with Andy Erickson hosting the panel discussion. We'll take a 5-minute break. We'll be back at 5 o'clock Minnesota time.
Great. Thanks, John.
Thank you very much.
Welcome back, everyone, to the Minnesota Stormwater Seminar Series. Thanks, David, for that wonderful presentation and setting the stage for this panel discussion. I'll ask the other panelists to start sharing their screens as I welcome and introduce everybody. Thanks again for joining us today. My name is Andy Erickson. I'll be moderating the panel discussion, and it's my privilege to introduce our local experts that have graciously agreed to join the panel and this discussion here with David. So our first panelist is Tom Hollenhorst, and he's a research landscape ecologist at the EPA Office of Research and Development and the Great Lakes Toxicology and Ecology Division Lab in Duluth. But he also is an adjunct scientist at the Natural Resources Research Institute in Duluth, as well as adjunct faculty in the Water Resources Science Graduate Program through UMD. That's the University of Minnesota of Duluth. So Tom, from your background and perspective and experience, how do you relate to this topic today?
Get my mute to work. Well, it's really exciting. And thanks, David, for your presentation. I really appreciate it. From my perspective, I'm thinking about watersheds and the networks of tributaries and that are flowing through wetlands, ponds, and reservoirs, and eventually into our stormwater systems, sometimes overwhelming our stormwater systems, and how this kind of thinking can start to mitigate some of those issues. I think there's all kinds of interesting applications for the type of technologies that David presented today in terms of smart agriculture, nutrient management, flood mitigation. It's just as we start to develop smart watersheds, which we're moving closer and closer to with these connected monitoring devices in real time, continuous, really gives us the potential to protect our waters and mitigate some of the flood damages and pollution and nutrient excesses that we've had. So it's great to see these developments coming along and then starting to think about how they'll scale.
Yeah, that's great. Scaling and thinking from the watershed, big picture perspective, right? That's a big deal. Very important for these systems. Thanks, Tom.
Yep.
Our next panelist is Anthony Aufdenkampe. He is a senior environmental scientist at LimnoTech. So Anthony, from your perspective and experience, how do you relate to this topic?
I think this is very exciting. I started getting involved with environmental IoT monitoring about a decade ago as kind of a spin-off from a National Science Foundation project when I was still operating as an academic. And just thinking about the potential for real-time control is just, the potential is really exciting. And what David just showed was much more than just potential, right? Before we could imagine it on paper, but David just presented a whole series of experiments with some pretty interesting and conclusive evidence. Real-time control is taking off in a number of cities, but primarily around sewer systems to prevent stormwater flooding, basically combined sewer overflows. They're trying to prevent that. And as Tom just said, the potential to apply these in rural infrastructure and elsewhere, I think is huge. And we think like, well, these are complicated, as David said, to install. That's true, but think about how much it costs to drive a bulldozer around for an extra day or two. The costs of IoT-based monitoring and control is actually pretty minimal compared to the cost of actually building these BMPs and green infrastructures, even in a rural context. So it's kind of always stunned me that so much of what we do has no monitoring connected to it when, you know, just for a few % more in the total project budget, typically you could install some monitoring at least.
That's great, Anthony. Thank you so much. And our next panelist is Ben Janke. Ben is a research associate who's co-affiliated with St. Anthony Falls Laboratory here at the University of Minnesota and the Department of Ecology, Evolution, and Behavior. So Ben, from your perspective and background and experience, how do you relate to this topic?
Yeah, thanks. I think my background is more in monitoring and data collection and less on the control side of things, even though that's always a thought that's occurred to me. And the advantage of being able to change the the configuration of the outlet structure of a pond. So I do a lot of work in ponds, and so that's kind of where my head is right now. But being able to draw down a pond before a storm, or even like say at the end of like in the fall, so that it can hold more snowmelt runoff in the spring, which is in our part of the world is going to be full of road salt, which is a huge problem. So thoughts like that, how we could use very simple kind of active controls on ponds at least has occurred to me. I've done a little bit of some of the low cost monitoring, and Anthony has actually helped kind of kick that off for us. I think having also been involved in a stormwater pond literature review that's still kind of in getting to the finishing stages on that, and John Gulliver's been involved with that too. But one of the topics that seems to have popped up a lot recently in the literature is this real-time control, and especially kind of looking at watershed scale. So how do you optimize the control? So, it's one thing to optimize the control for a single rain garden or a biofiltration cell, but how do you optimize all those throughout a watershed to achieve some goal at your outlet at bigger scale? And there seems to be quite a lot of work going on there, but a lot of it's like machine learning, data-driven, kind of data-hungry sort of tactics, which are not going to be readily implemented anytime soon. Anyway, so I guess that's kind of where my head is at.
That's great, Ben. Thank you so much. I want to ask for David's relation to the topic, because he set the stage, right? He set the tone for the discussion today. So I'm going to dive in with a question. Again, if you're here in the audience live, please post questions in the Q&A so we can ask them of the panel and get their perspectives. We want to tie this together, not only learn from David and what he had, bring it to Minnesota, but then bring it also beyond our Minnesota borders as well. So thinking big scale, on these questions. And the first question I want to ask is thinking about, again, real-time control, but also just remote sensing, in situ monitoring, big data. It seems like Ben mentioned in the literature, real-time control is showing up. And as Anthony mentioned, a lot of these Enviro DIY and low-cost measurement sensors and systems are going in place. And so we are collecting a lot of data on our stormwater systems. And so the question I want to ask is about, what benefits have you seen with this large increase in remote sensing, in situ monitoring, even real-time control, and other kind of data-driven stormwater management techniques? And I'll offer anybody on the panel can jump in at any time. So what do you think are these big benefits we see out of these systems?
I can comment.
Yeah.
A large scale on the Great Lakes, the Great Lakes Observing System is a smart Great Lakes initiative, collaborating with folks like the Cleveland Water Alliance and others to really think about how we can integrate all of this monitoring data that's collected from so many different sources, from local, state, federal agencies, universities, combining those in situ data sets with remotely sensed data. And then this type of real-time monitoring, continuous monitoring on streams and tributaries to think about loads to the nearshore in the Great Lakes and how they may affect harmful algal blooms and things. And, in the case of Toledo, Ohio, and what was it, 2014, these are really big questions. Combined sewer overflows is another big issue in that regard too, that I think these kinds of approaches are really, I think Ben may have mentioned that, but really where we need to go.
I'll add that the benefits of real-time monitoring are really extremely numerous. Real-time monitoring alone has a certain set of benefits, but if you kind of think of them in kind of a holistic system of monitoring, like Tom was referring to, then things really shine. So often we do modeling work in isolation of real data. Maybe we have a few data points at a few times, but most materials move on the earth during short duration storm events, right? So capturing that from a sampling program is challenging. If you real-time monitoring can't handle everything, right? Real-time monitoring for something like E. coli or even nitrate is really quite challenging if it exists at all. It's really still a research topic. And yet, if you have real-time monitoring for things like just water level and maybe even something simple like temperature conductivity, but if you can get a turbidity sensor out there, suddenly you have a way to connect the dots between your samples. There's lots of work that shows multivariate regressions, even newer, fancier multivariate machine learning approaches where you can predict things like total phosphorus from turbidity, conductivity, temperature, and water level. There's a handful, like literally a half dozen papers on that. There are, and then on top of it, if you've got a sampling program, it's really helpful. This is how I got into it more than a decade ago. We were doing storm chasing at a bunch of sites, and to time when we got out there, when we triggered ISCOs, when we filled barrels of water, having that real-time capability was just transformative in how we actually sampled for the things that we still had to fill water bottles for. So there's like a whole family. And then when you add to it the capabilities that we have with these tiny little microcontrollers to actually actuate motors or pumps, then the world is our oyster.
If I could just jump in, Anthony, that was great. I completely agree. I would say that from my little world, and I could probably come from more of a research background, but the ability now to understand spatially representative information throughout our networks, whether that be just having turbidity sensors, we put 10 of them in this wetland, and before this kind of sensing, all these cheap sensors were available, we couldn't do that. It was just too cost prohibitive. And now we're thinking of putting 30 in there and understanding treatment mechanisms throughout that wetland. You know, how well are those macrophytes, you know, macrophyte areas kind of reducing sediment levels, you know, how those open water sections of the wetland potentially increasing turbidity levels in the water column. I think that kind of thing is for us really interesting. So a little bit more sophisticated understanding of how these things are operating, which really hasn't been done in field scale very well prior to, well, not that I know of anyway. And the other thing is, you know, we're now using these little sensors throughout stormwater networks and placing them in 30, 40 different locations to try to understand where sources of, you know, incorrect connections are coming from. We can use them to train our models better, get better understanding of hydrological responses. You know, yeah, I think for me, I get a little bit overwhelmed with the amount of data that can come in. And I think that's probably another question about how do you, in particular from these low cost sensors where we can maybe accept a lower level of reliability or performance perhaps, because they're so spatially representative, you're getting really good bang for your buck. But how do we ensure that data that's coming in is still of good quality, that we can then go and, you know, respond to that change? And so we're thinking about redundancy, we're thinking about digital twin models to confirm data, we're thinking about lots of things to deal with that immense amount of data, which is difficult to understand, but also may have uncertainties in it that we don't really quite comprehend, and we could do something in the wrong way if we don't manage that uncertainty. So anyway, just
I might add something about kind of the remote sensing piece, which is a little bit different because those data are also starting to be collected at higher temporal resolution with satellites being able to do daily flyovers and things like that. You know, and in some of our work, we've benefited from having lots of aerial imagery or LiDAR data. You know, there's a LiDAR point cloud for the entire state of Minnesota, you know, with canopy returns and things like that. So we've used that to assess canopy sheltering around ponds, or even just topographic sheltering around stormwater ponds. And that's been beneficial for being able to assess a lot of sites where we might have some of these, especially sites where we have these stations set up that are collecting data at high resolution, where we can see changes in wind and changes in mixing and things in the ponds, but being able to relate that very, you know, without having to go out and survey trees. You know, there's you know, these spatial data sets, and using some of these also for assessing vegetation cover or duckweed cover in the ponds, which is kind of emerging as a really important factor for phosphorus at least. So I suppose I should mention that I have very much a kind of phosphorus and chloride bias, I guess, in the work I do, in addition to being biased towards ponds. But the sort of remote sensing data sets have been incredibly useful.
Go ahead, Tom. Yeah.
It's interesting to think, Ben, how we can, with these types of tools and technology, we can not just model, but really measure the benefits of a single tree or urban canopy or a neighborhood's amount of canopy, both in, you know, flows, volume, but temperature, and all those kinds of things. We spent a lot of time thinking about restoration work and restoration effectiveness. And if you're doing wetland restoration in a watershed, and you may have 6 or 8 different projects going on in a particular watershed, but it's still really hard to measure and see the effectiveness of those restorations. So I think these are the types of tools we need.
And I think go ahead.
We did some work with water level recorders in Duluth. And I think Tiff Sprague was on the call, and initially she was looking at, you know, I think 30-minute increments, and then 20 or 15-minute, and eventually I think landed on 10-minute. Because some of these small streams are so fast, I mean flashy, that they change really quickly.
Yeah, I think, and I want to come back. I'm going to come back to I want to ask questions about the variability, and because David, you mentioned that, and then the big data question, how do we deal with these big data sets and things? But we have a question from the audience that I want to ask, and then we'll circle back. So this question actually comes in from Bert Van Doon. Thanks, Bert, for joining us today and asking a question. So David, but I'm gonna expand this to the panel as well. But so David, for where things are in Australia, or where are things at in Australia to moving from this academic exercise to actual implementation in a municipal context or in the cities? And what are the needs from the QA/QC perspective to make that work? Are you getting any challenges from the cities in trying to implement or not?
Great, thanks Andy, and thanks Bert for your comment. I appreciate that a lot. And thanks for sharing that link before, Bert, on your Albertan public health guidelines. So we know about Alberta's work in this space, so thanks for that. In terms of what's happening in Australia, I probably can't speak for the whole of Australia, but I can certainly speak for the state of Victoria. At the moment, our main industry partners in this space are Southeast Water and Melbourne Water. And I can tell you that they're very excited about the concept of real-time monitoring and control of these assets, of water-sensitive or green infrastructure assets, but they're apprehensive and a bit nervous about some of the implementation of these types of assets. So I'll talk about a couple of examples where things are going very smoothly and fast, and some where we're going to take a more cautious approach. So I mentioned a group called Tank Talk. If you're interested, have a Google of that. Tank Talk by Southeast Water in Melbourne. That's controlling different tanks in a system in a municipal catchment to achieve better storage capacities of rainwater tanks before an event comes. They're hoping to have a better overall impact on downstream ecosystems by doing that, by removing that water, therefore potentially restoring base flows by leaking tanks, and also ensuring that we don't get such flashy flows into our downstream ecosystems. So have a look at that. That's happening. That's happening at a scale which is, I would say, municipal. And it's also being researched in a developing catchment in Monbulk Creek by Tim Fletcher and his crew at University of Melbourne, doing a lot of this rainwater tank control, in particular for better hydrological responses. So that's pretty exciting. So from a stormwater perspective, that's going ahead well. Southeast Water are involved in lots of other real-time monitoring and control. For example, real-time monitoring and control of pressure sewers to reduce the impact on sewage treatment plants downstream, to kind of control that peakiness that occurs in our sewer systems. From a stormwater wetland perspective, I just mentioned we've got this grant with Southeast Water and Melbourne Water. They're very excited about we've got something like 10,000 or 5,000 not performing optimally, and there's a good lot of benefits, even if we can just control the water levels better in those wetlands so the vegetation health becomes better, then I think that is even an exciting opportunity for Melbourne Water. And that's kind of where we're going to start. We're going to start slow, and we're going to demonstrate to them by actively controlling these assets, which we've never done before in Melbourne, and they're big assets that could cause. We're going to start slow, do things, show them. We're going to reduce the water level by this kind of the conversations that we're having at the moment. They're very excited. We're going to take a cautious approach, though. From a QA/QC perspective, there's a lot that we're considering. As I mentioned before, redundancy in water monitoring networks, ensuring that we have multiple types of, in particular, water level measurements. So ultrasonic, radar, depth pressure transducers, we're going to put them all out there so that we really know what's going on. We're even setting up cameras because we want to make sure that things are going to go very well and very smoothly. We're not going to harm the local residents. If you really want probably the most active control strategies that I've seen, go to Branko Kirkutz's website from University of Michigan. He has gone to the point of where he's had his students controlling a stream so that the stream hydrograph makes an M for University of Michigan. And when I saw that, I said, wow, So if you want to have a chat, Bert, to someone who has implemented something in a municipal, highly dense area, right? Municipal context of real-time monitoring and control, have a chat to Branko. He's made it done. I don't know how he's done it, but he's done it. And I think, we can learn a lot from the way he's implemented that in his state. So
That's great, David. Yeah, Anthony, I was just going to turn to the panelists. How are we seeing it locally? Go ahead.
Yeah, to respond to Bert's question about the second question about QA/QC needs, I just want to point out that, these little environmental IoT devices that cost, these are super capable data loggers that cost like less than $100. They can connect to any sensor. So if you want to put an $18,000 sensor on there, you can put a $5 sensor on there. So the QA/QC questions are all about the sensor. All this thing does is that it collects the bits and the bytes and the numbers and then transmits them via radio to a data server somewhere. So there's always a lot of questions about how IoT might affect data quality. And the answer is, it doesn't. It all depends on the sensor. The same practices that you would do, for, let's say, one purpose, operate whether or not you've got a $5,000 data logging station with solar panel, or whether or not you've got a little tiny one that's $350 for solar panel and batteries included. So that's the first thing. The second one is that I'm working with a utility, a wastewater utility that's discharging, that's working like with water reuse questions in Oregon. And I was working kind of with their digital solutions team, the ones that are trying to be innovative and kind of implement smart water. And of course, they've got many other teams at a utility, a big organization like that. And so they're people who are in charge of water quality and meeting regulatory requirements. We're very skeptical about the kinds of sensors we were introducing. The sensors that these bare wire sensors that can be plugged into anything, had capabilities to be calibrated. And it turned out if they applied the exact same practices, cleaned them with the same frequency, calibrated them the same way, their data quality was identical for sensors that were 3 to 5 times or 10 times less expensive than the brand names that they were familiar with. So throwing that out there. And so they went ahead and purchased $100,000 worth of these sensors from China that I recommended to them, just to give you an idea. Like after a year of testing them alongside YSI and Telog, they were like, yeah, these are good.
That's exciting to hear. Yeah, and it's good to see those kind of examples. Any other comments on kind of local adoption, local implementation, or even barriers or kind of hesitancy on doing some of these big data collection and even real-time control?
One of the things that I've been thinking about and trying to get to, and I'll put a link, EPA just came out with a report about participatory science and a vision for participatory science. They're starting to think about things like equipment, lending libraries, and things like that. But imagine if, we can equip homeowners in urban areas with these low-cost sensors, minimal amount of training, but engage them that way so that they're really engaged, just like people getting, weather sensors and participating in the NWS COOP system. So they're doing that for streams, and they're adopting, a stream that flows through their backyard or nearby, and putting out these sensors seasonally as needed, and then watching the data just like they watch the weather. I think we're right on the cusp of that and seeing it happen. And you see it now with the National Water Model. If I point that out to some friends that paddle and like whitewater, and if you look at the National Water Model and on the Esri Arc Online Living Atlas, you can see every 3-hour prediction of what the flows are for any river mapped in the NHD system in the United States. That's pretty amazing. People love watching it.
Well, I think, yeah, that's been something that's in recent decades, the availability of data, right? And in real-time data, yes, we had data you could download and deal with, but now you can see up to the minute data on so many systems, even in our neighborhoods. So I can see how people will get excited about that. Any other comments or thoughts on this idea of implementation of real-time control or even monitoring and low cost data collection systems?
I'll just jump in there, Andy, if I could. Just one quick one is, I think for us, we are focusing on, as much as possible, non-contact sensing. And the reason is not that we think we can get better data. In fact, we know it's not going to be as good. Well, we hypothesize it's not going to be as good. But the reason is from a maintenance perspective. And so I suppose once we start talking about lots of different sensors in our networks, the increased load on our utilities or whoever it is going out there to maintain those sensors is a big deal. Turbidity sensors, I don't know about you all, but I have some situations where I don't need to maintain a turbidity sensor for a month. But in other situations, if I'm not there each week, I'm not getting good, reliable data. So it's a really, turbidity is hard. You know, depth sensing, EC, like electric conductivity, temperature, you know, they're pretty stable, and you know, you're pretty. I'm okay with them being in the water, but I think as much as possible, if we can move outside of the water column, we can really reduce that maintenance frequency for gathering all of this data. And so where our team is kind of focusing on, you know, can we get any information about turbidity sensing from out of water sensors, you know, non-contact sensors. I mentioned the radar and depth sensing technologies that we're kind of working on. And I just suppose I'd be interested in anyone online who's kind of moving down that pathway for the same reasons as I am, which is that, you know, maintaining and installing such a diverse network of sensors is just a really big pain in the butt. So that's just something I was thinking of as the discussion.
No, I think that maintenance piece is an important part of it, right? As Anthony was saying, it's the data, the QA/QC is really dependent on the sensors. And one aspect of that is not only the quality of the sensor, but is it maintained? Is it properly calibrated when it needs to be calibrated? Is, you know, all of that is important. So that is going to have a big impact on your QA/QC. So if I can, I'm gonna go back to a couple of things that was mentioned, and this was something that was rattling around in my mind. What would you say, if anything, maybe this increased data collection techniques, these technologies, the sensors, the fact that we have them everywhere and collecting all this data, what do you think that's taught us about the variability in our stormwater parameters? You know, you mentioned it earlier about well, we saw it in David's presentation, right? The variability in the data that we see. Are we getting better data, or do we know these things better? Or are we really just quantifying the fact that there's so much variability in these parameters, both flow parameters and water quality? And what would you say to that?
Well, I've got an example because I was thinking about looking at this data just yesterday. You know, this in our pond monitoring, we typically have a station that's measuring a temperature profile, you know, at maybe 5 or 10 minute intervals. And then periodically we go out with a crew, maybe every 2 weeks, do a profile by hand of temperature, oxygen, conductivity. When we were originally looking at those, you know, weekly profiles, we thought, oh, these ponds are stratified all summer. We were shocked to find how many of them were strongly stratified, even when they're only, you know, a meter or 2 deep. But then when we started digging into that, you know, 10-minute data, we realized that the top layer of the pond, maybe the top, you know, half meter or so, is actually mixing on a diurnal basis, as you might expect. Does that matter? I don't know. We're still kind of trying to figure that out, but there's more dynamics to it, even in these little ponds that are heavily sheltered, than we thought. And so we're still kind of working through that, and certainly, you know, trying to relate maybe the mixing depth on a given day back to the wind speed. So then if you really want a pond to mix and stay oxygenated, because that's kind of a phosphorus management issue, you know, then that information could potentially be helpful. You know, if we can relate the mixing depth to how much topographic or canopy sheltering there is, or duckweed cover, because it seems like a lot of these ponds, once they're fully covered in duckweed, they just stay stratified and the dynamics kind of attenuate a little bit. So that's an example of you know, something that was kind of revealed to us once we started looking at these data. I'm not sure what you do from a real-time control standpoint with that information, or what it gives you, but it, at least as a scientist, it's interesting.
Your comments, Ben, remind me of some work we've been doing. We have these autonomous underwater gliders that we're deploying in the Great Lakes. And like all of, the science, the variability is what's so telling, right? So we've been looking now at the dissolved oxygen and chlorophyll data in a diurnal way. And then from that, you can start to look at rates of respiration and production and start to get at some really basic measures, estimates of primary production. First at these really small scales, but now suddenly we can start thinking at some really broad scales across the Great Lakes or across a Great Lake. So I think it's the change that's interesting. And it's at all scales, right? We have diurnal, seasonal, annual, decadal.
We've been experiencing some interesting turbidity readings that we've never been able to capture before, and thinking, is this our sensor, mucking up? And, we're getting this variability that we've never seen before in some of our readings. And, my student Meow, who's online right now, we automatically jump to the assumption that actually it's probably our sensor that's not working. But we don't know. You don't know if it's this sensor just behaving erratically compared to another sensor that we've got side by side. So this variability question is really interesting. We're getting data that we've never seen before, well, not me anyway. And sometimes, as I said before, I'm kind of shocked and worried about how I'm going to process this data. Is it wrong? Is it right? This variability is very interesting for us.
Back when I was doing academic research, some of the first turbidity stations and stream stations we put in, we were seeing a doubling of nighttime base flow turbidity, kind of just a blanket across the board. And a grad student actually did some experiments, and we determined pretty conclusively that it was nocturnal invertebrates such as crayfish and maybe some vertebrates too, that were basically stirring things up at night. And we could totally see when animals like raccoons came to the stream. In fact, we'd see these like in the middle of this kind of just like baseline elevation at night of turbidity and at base flow, we'd see these huge spikes that would come by, and we were logging at 5 minutes. I would say that if you're not logging at 15 minutes or less in a small stream, you might as well give up. Our standard is now 10 minutes, and we go for small streams, you do 5-minute intervals. And we started recognizing that, and we'd go stream because it was nearby, and we could see raccoon tracks like upstream. So we're convinced that there's all sorts of stuff that you can see when you start looking, right? We never used to look. We used to pretend that, this is the average. My measurements every 2 weeks at base flow represent an average condition, and it's not at all true.
So in other words, if I'm going to sum that up, by having more data, shorter time steps, and having a lot more of this information, we actually would rather not know because we have more questions now than what we had before. We can't even test the hypotheses that we come in with. We have to come up with more reasons to explain the odd data that we're seeing. But actually, that leads to my next question. I wanted to talk about, so that's variability, and that's adding this. What about if we have, and this gets back to one of the questions from the audience on citizen science, what if we have multiple sources of this data within a watershed, right? What can we do to combine these data? If they're collected by multiple different ways, different methods, different types of sensors, are there good ways to do that? Are there lessons that you've learned when you've tried to do this? Or what would you say to that piece of trying to combine these data sets where it's coming from all over? If anything, I guess.
Well, I could say that, working on a project right now, aggregating stormwater monitoring data sets from across. Originally, we cast a pretty wide net, the entire state of Minnesota, and ended up with more than we could handle just in the metro of Minneapolis, St. Paul. And most of those data sets are collected by cities, watershed districts, counties that are kind of following more or less the same protocols, using a lot of the same analytical labs to do their analyses. And it's been a huge undertaking just to get those data sets, which should be very similar, in a format that can be analyzed and matched up. So I don't want to throw water on this question, but yeah, I've been struggling with that. So if anyone has some suggestions for aggregating even like more disparate data sets, that I'm all ears.
That's a perennial challenge. I think there's some solutions out there, and I'm gonna do a little bit of a segue and go into this like big data, this idea of being overwhelmed by a mountain of data. And I will make a plug to all the faculty members out there that in every one of your programs, you should have a data science class in Python or R required for your graduates. And for all of you who are hiring people to help you with water management, you should start looking for that in their qualifications. Being able to automate pipelines for data analysis and visualization is absolutely critical for us to deal with any of these things that we're talking about. And like LimnoTech, it's kind of, it is starting to become okay, if this person doesn't have these capabilities, like why do we want to hire them? I mean, sometimes there are good reasons why we want to hire them, but we know that the people who have those capabilities are very, very busy in our company.
I think that's a really good point. Automating systems, data collection, or data management is going to be a big piece, because that can be the bottleneck, is the people having to manage the data. Tom, go ahead.
Well, as we've been thinking about participatory science in EPA, and as we encourage citizens to participate and collect that, how do we maintain that engagement and, really step up our side of the bargain and use that information in decision making, which is a real challenge. So we've talked about possibly a tiered approach where, one level is kind of informative, we're engaging people, we're getting them excited about science. At another level, maybe the quality assurance plans are more in place, the calibrations are there, it can be used for planning and a higher level of decision making, and then up that tier until you get to permitting, regulatory needs, and so forth. And I think as organization, the key is supporting long-term and financing and funding long-term the organizations that are going to really organize the collection of that data, so they can get to the level where the data is organized well enough so that, and calibrated, et cetera, quality is good enough for that higher level of decision making.
Just to add, not to discount everything that's said, I completely agree with everything. It's funny that our engineering degree, Anthony's just removed its only data analysis subject, which is really disappointing considering the movements that are occurring in this space. I'm trying to work to get that back in. I think one thing that we can use to kind of reconcile data sets that come from different sources, and as you mentioned, Andy, I think, this concept of digital twinning, which is not, it's just a new name, it's something that we've always done, I think. Well, that's what I feel anyway. We often come up with these new whiz-bang names that sound awesome, but it's really just commonly used. I think that concept of modeling a system, modeling inputs into a system and different data sources, and then reconciling them to kind of figure out or, go to the next step of maybe mitigation, maybe a control strategy or something like that. The idea of using models to reconcile data sources, I think, is something that we could probably do. And I know there's a few people like Franco, as I've mentioned already today, his name, and also some people from DTU, the Danish Technical University, are doing some really nice digital twinning models to combine data sets.
Any other comments or thoughts on that?
I was just going to comment that we're in the midst of a inter-lab comparison on some water quality data that's, total phosphorus, soluble phosphorus, nitrogen, and from different labs, sometimes different methods. And it's kind of frustrating. It's what we're seeing so far. So when we're trying to really integrate across different groups and things like that, it's a big challenge. And we're just starting to think about that too in terms of our SON data and things too, making sure we're comparing our groups.
Circling back to real-time control, I think that for many of the purposes that David talked about, we don't have to have fabulously accurate data, right? We're looking for dynamics. Did the water go up or down? How quickly? Is it time to like pull the plug on the drain and let it drain out by 30%? That kind of stuff. And if you're off, by a centimeter or an inch or whatever, like, does it matter? Right. So one has to kind of think about what data quality do you really need for your purpose, right? If you just go down the rabbit hole of we need to have quality data. Well, if you're trying to maintain a water quality discharge permit, yes. And if you got the regulators looking at you, you jump through all those hoops. But if you're trying to just like double your efficiency in your stormwater wetland because, by doing some type of real-time control, you probably don't need that super high level of quality.
Great point, Anthony. I reckon your first point there in terms of, often we're just looking for relative change, and so our sensors, one of the cheapest sensors we had for depth measurement was horrible. It was drifting like really bad. But what we were after was actually relative changes and patterns and trends. So yeah, I completely agree, Anthony. That's something that we need to consider, the quality of data we need.
That actually is reflected in a question that just came in as well. How do we reconcile big data and the KISS principle, right? Which is the keep it simple, stupid principle. And I'm usually the stupid that's not keeping it simple in that phrase. But so I guess what would you add to that? Anything else, that balance of accuracy and quality, but then your effort, your level of effort that you have to put in and what you need for your application.
All right, I just say one thing about the big data, and I made a plug for data science, right? And we think of data science, like there are lots of people talking about data science and machine learning, and some of this stuff is kind of crazy, and so it can be a little overwhelming. But I will say that the reason Python and R have kind of, everyone's teaching them is because they're actually super easy to use, and every month some new, the reason they're easy to use is because they have these like high-level functions, these libraries that do a lot of this stuff for you. So once you learn a little bit of the basics, and then you learn about these libraries that might be useful, creating this really cool interactive multi-dimensional plot of something looks like that could have taken a whole PhD not that long ago just to create the plotting functions, but now it's like 3 lines of code. And I really encourage I was encouraging, think about the young people and training them in, but actually any of you on this call, if you know how to type in a formula in Excel, probably could take a 16-hour online course and start doing much more sophisticated data analysis than you ever thought that you could possibly do before with 16 hours of investment. And I'm not joking. We're doing some of that right now with our staff and some of the people I work with.
Other thoughts on that?
What I think a lot too is setting up the data management systems and the data flows and the data archiving systems makes what Anthony's describing a lot easier, so that we can write APIs and things to go to the data sets and pull them down to hopefully simple applications.
My comment here is more about the control maybe than the big data, but I think the keep it simple, stupid concept for us, we really emphasized on that. Like, we really want to make sure that the first implementations of real-time control for these systems in our neck of the woods is simple and easy, even if it's not an optimized solution. We don't want to scare people away. We don't want to scare this off saying, okay, this is so complicated that you need a hardcore model predictive control strategy that uses all of this information to then come out with a control output. I don't think that's not the way we got to where we are today with green infrastructure. You know, my predecessors, they all worked on this concept of making sure there was good guidance, it was logically done, there was models and guidelines that supported the implementation of what we call WUSUD or GI, green infrastructure. And I think if they had done it in the way which we think would have achieved the best outcome, then I don't think we would have been where we are today. I think there was a compromise of, you know, what do we need, where do we need to get to, and how do we need to get there, I think are really important questions. And I don't think going for the optimal design first is the strategy. I much prefer, let's educate ourselves, figure out how this whole ecosystem works, and then build on that and make it better with time. I'm really not a guy who wants to go for the best at the start. It's just, yeah, I think that could put the industry back.
Maybe that's an argument for keeping the academics out of it, since we can. Maybe I'll just speak for myself, that I can get pretty lost in the weeds, you know, the details of a data set, and the bigger the data set, the better. When sometimes, like you said, David, it makes sense to maybe work backwards. You know, if you have some goal in mind and you could change the way something is controlled and get some improvement, it may not be the most improvement you could get, but as long as it's an improvement, you're taking a step in the right direction. Because, you know, trying to get it all at once, yeah, I feel like that's maybe the academic approach, is like, well, we could do it the best, so why don't we? You know, and sometimes maybe 80% or whatever, 50% is good enough for starters, and you work from there, because you always learn in the process too.
That's a really good point, and leads to the I'm going to ask one more question, and then we'll do the final question after that. And that question is, so how would we as experts, and I'm saying collectively, this is anybody on the call, but how would we as experts kind of boil this down for decision makers, right? Because as Ben was just saying, we can spend a lot of time in the data, we can look at all these interesting things and look at diurnal cycles and all this, but oftentimes we need to boil that down for the people that need to make decisions on how to manage their stormwater resources. So that's my question. How do we translate this? How do we boil it down? How do we simplify it to give people guidance to improve the management of their system? So what would you say to that?
I don't know if this exactly answers your question, Andy, but what we did was we started off with the worst performing wetland in Melbourne. And we said, guys, give us this wetland. And it's already bad. We're unlikely to make it worse. And give us this wetland for 6 months, see what we can do. If we can increase the performance of the vegetation, make it healthier, let's just make it simple. Let's just focus on vegetation health. We improve that vegetation health is improving just by some better management of the levels within the wetland. Then that's the first step. If you're happy with that, then we can continue looking at other wetlands. But our strategy was, very simply, give us something that's broke, and we're not going to break it well, and we're going to learn from that, and you're going to come along with us with that path. That was our strategy.
For us, it's been, a monitoring first approach, and I think that pairing systems, maybe one disturbed, one natural, a reference condition, and then disturbed, and then monitoring that with these types of devices and technology, a continuous high frequency before we get to the control. I think we think a lot about this natural flood management and slowing the flow in watersheds, and adding storage into the system and restoring wetlands. So I guess that's some of that control, I guess, in terms of restoring the wetlands, but is it having a good effect, a measurable effect? But then I can start to think about, we're trying to, in that context, thinking about desynchronizing the flows from the headwaters, right? All the different headwaters in a watershed. If we start to bring a little bit of control to that, maybe that really does help us in terms of some flood management. And we see it, in other places, the waterfowl refuges are controlling water in their wetlands all the time, constantly, and seasonal drawdowns and things like that. So, yeah, that's pretty exciting. I really enjoyed the conversation.
I think, one thing that could be helpful for implementation is find somebody who's brave enough to try this and then learn lessons from it, and puts a little bit of the pressure on those folks to kind of present their lessons learned and steps along the way. But I'm thinking of, the Capital Region Watershed District has at least one pond with a real-time control on the outlet because it's an undersized pond and they didn't have any room to expand it because it's in a park. And so they put this valve that they control based on weather forecasts to drain the pond out, and then it can hold more water. And as far as I know, it's working pretty well. And my apologies to Cap Region people who are on this call, and I've gotten part of that wrong. But so any lessons learned from something like that, a demonstration project, I think really helps people, would help with the implementation if they can see, oh, this does actually work, and there's some promise there.
Yeah, go ahead. Any other thoughts on that?
Just along what Ben said, is it's going to be demonstration projects and pilot projects where we can demonstrate for communities that this can work. There's affordable solutions out there.
I think our idea is to use this wetland as a case study and then use that to develop guidance documents for wider spread implementation. I think that's really important.
Yeah, and I love that example of taking, the worst wetland. You can't break it anymore, right? So let's learn some things from it. And I'm going to encourage, anybody that's in the audience, if you have a site that is just a disaster and you're not sure why, bring in some people to study it, because there can be a lot of lessons learned and a lot of understanding and a lot of guidance that then helps prevent that from happening in the future. Some of the best research projects that I feel like we've done have been on that type of situation where, we didn't understand what was going wrong, but we learned what was going wrong through the research and collecting a lot of really good data, a lot of detailed data that maybe, very simple methods didn't always give us the reasons. So I'm going to take that and transition into our closing question for our panel members. And that closing question is, what key takeaways would each of you give to our audience based on this discussion today? What do you want them to walk away with that maybe they can use to help improve their water resources, their ecosystem health, even the quality of life for residents in their jurisdictions? And we're going to do this in the same order that I introduced our panelists. So Tom, you are our leadoff hitter. Take it away with what are your key takeaways?
Well, just that there's some really exciting technology on the horizon, and it's accessible. And that provides a lot of opportunities for engagement with our communities. We can bring this to them with demonstration projects, pilot projects, and we can engage them with citizen science. So
that's great.
Opportunities. Nope, that's all.
That's great, Tom. Thank you so much. Anthony, what would be your key takeaways for our audience today?
I think I'm going to follow up on Tom's thing about accessibility. Environmental IoT used to be just kind of on the cutting edge of research, but now there's actually a ton of companies that are doing these things. Some of these are pretty easy to program. Some of them, like the ones that David showed and that I've been using, use the Arduino framework, which a lot of high school and college kids learn how to program. They're not super complicated to do some simple stuff. But there are commercial companies now that are also in this space, and that wasn't true 2-3 years ago. So now is the time to start trying some of these things, especially based on studies from the literature that David's group's producing, other groups are producing, Branko Kirk has his group, et cetera.
That's great. Ben, what would you say are your key takeaways from today, or what would you recommend for our audience?
Yeah, I'm not sure I have a whole lot to add to that, because I think that kind of what Anthony said at the beginning about, there isn't anything special about, or there isn't anything inherently different about these systems, except that the data logger part of it is cheap. If you want to hook an $18,000 real-time nitrate sensor to it, great. There are ways to do it cheaper. And so just thinking about that, and that does make it more accessible as a research tool. But I guess I'm interested in seeing more applications kind of out in the real world. So this is maybe not quite getting at your question, of takeaways, but I think I'm really excited to see, more demonstration projects and see where these things, pop up in practice. And I know there's some other folks in the Twin Cities who have been implementing these kinds of things, and my apologies for not mentioning those projects, but yeah, I'm just kind of excited to see where this goes, because I think there's a lot of promise for retrofitting existing structures that are maybe not working very well, and so that you don't have to kind of build a better mousetrap or redesign the wheel. One of those things, if there's a way to kind of adapt to what we have and make it work better, that's helping, until we can come up with maybe a better solution.
No, I think that's great. It's another tool in our toolbox, right? And we got to try it. We got to learn from it and use it in ways to help us make better decisions at the end of the day. So David, you led us off. You now get the final word. What would be your key takeaways today for us?
I think everything that's been said, I agree with. So I love all the other takeaway messages. I think the most important one, though, is to kind of give this concept of low cost or IoT for water kind of concepts a try. I think don't be afraid. I think we've discussed a lot of the uncertainties already today. I think you could, if you're interested in it, then clearly Anthony and his group and lots of others around the world are able to help out, provide some sensors. If you reach out to me, I'm happy to send some to anyone to trial, and I think you'll be pleasantly surprised. So if you're a bit apprehensive about jumping into this market or this space, then I think my suggestion would be to reach out to someone, get some freebies and give it a shot, and I think you'll be pleasantly surprised. And what's the harm? Put it next to your best sensor, have a shot, and I think you'll be happy person. But I also want to say, moving on from real-time monitoring to real-time control, I think real-time control really has a lot of benefits. And we've spent a lot of the discussion talking about monitoring and low-cost devices, which is a really important part of that process. But I think real-time control, I think, is really an important thing to start integrating into our design thinking process. And so I ask everyone to kind of take that message back and start thinking not just about what plants you're going to put in, what kind of vegetation and what type of soils you're going to use in your next design, but also how can you potentially incorporate some exploration of real-time control. And it doesn't have to be complicated.
I think those are great words. And as Ben mentioned and others mentioned, there are some examples locally and around you that are doing real-time control. So let's learn from each other and see how those are working and how we could implement them throughout our systems where it makes a lot of sense. So with that, I want to close the panel. First, I'm going to thank our panelists for joining. Anthony, Tom, and Ben, thank you so much for being on the local panel. David, of course, thank you so much for setting our keynote talk and setting the stage for this discussion. And of course, I want to thank you, the audience, for joining us today. Without the audience, without your questions, we wouldn't have a reason to be here. So we want to thank you for that. Thank you for joining. Please check out the schedule and look for future seminars that are coming up. Looking for future events. If you're interested in hearing about this, if you heard about this some other way and you want to know how to sign up, I'm going to drop some links in the chat. for how you can sign up and get notifications on this. So with that, I will thank you for your time today. Thank you so much. Enjoy the rest of your day, and I look forward to seeing you at a future Minnesota Stormwater Seminar Series. Goodbye for now.